This video will present our final challenge from Manchester Robotics. We are Team 6 from TechSem, and the members of the team are Jair Ulises Villacamorlinga and Eduardo Lopez Guerrero. So the main objective about this challenge was to use acquired knowledge from the course Robotics Foundation to design a closed-loop PID controller for a DC motor angular velocity using ROS and micro-ROS. In this slide, we can see a hardware list of all the components used for the final challenge. The important part is the right side, an electrical diagram that shows all the electrical connections that made this challenge possible. Moving on, we show all the software used for the solution. That was ROS, Ubuntu, IDE of Arduino, micro-ROS, and the virtual machine generator that is VMware.
If we are going to control the angular velocity of our motor, we first get to understand its output. We graphed here the velocity based on the PMW duty cycle, and we can see that it's a non-linear behavior. We have dead cells, we have different behaviors for the positive side and for the negative. Positive and negative represent basically rotation from one side or the other, and we decided to use a linear approach to this problem on this red part that is a linear zone that we appreciated that we can model our motor and establish some gains, some values to start to control the velocity or the behavior of our motor. For our next steps, we decided to analyze the output of the velocity in this linear part that we detected of our motor. We can see on the left side the output data of the motor, the velocity. It has a lot of noise, and we decided to use a mobile filter to filter out some noise and have a smoother signal so we are able to control properly the motor. It's on the right side, and we're moving on to obtaining the transfer function. If we want to control our motor, we need to get the transfer function. From our graph, we can approximate our transfer function or how we can manipulate or estimate that a motor is going to behave. We obtain the following value represented by G of S, and here it is, the graph that helped us determine this value. We got all of these, and now we can start to do some control.
Initially, for reference, we used Shinkorn's Reswick and Ziegler and Nichols method so that we can get initial PID gains. Using Castaño's method to obtain sample time, we obtained values between 24 and 12 hertz. But finally, we decided to use 16 hertz.
We created a program to analyze and get data of our performance metrics, and after PID gain tuning, we obtained our best result on the lower part of the table shown. In this final slide, we can see all the results. From a square signal type, we can see the motor velocity is catching up with the signal, and we got a good response. And on the lower part, we got a step response to a 4 radians per second velocity.
In this slide, we show a sine wave and a sawtooth signal as an input.
The thing we learned the most was ROS2, how to use nodes and topics, micro-ROS, the implementation on microcontrollers, mainly SP32, and how to implement all these tools and technologies for a PID controller of the angular velocity of a motor. Thank you very much for your attention. This was our final challenge for Manchester Robotics.